This question is from GATE 2016, Mechanical Engineering paper, Set 1, question number 37. A solid disc with radius A is connected to a spring at a point D above the center of the disc as shown in this figure. The other end of the spring is fixed to the vertical wall. Disc is free to roll without slipping on the ground. Mass of the disc is m and spring constant is k. The polar moment of inertia for the disc about its center is J equal to capital M A square by 2. The natural frequency of this system in radians per second is given by. For the given dynamic system and the given dynamic motion of the parts in the system, we will have to find out the natural frequency of the complete system. So we will form the equation of motion first and then we can find out natural frequency omega n by using the general expression. Let's use the Lagrangian method here to form the equation of motion. We know that Lagrangian L is equal to kinetic energy of the system minus its potential energy. And then to formulate the equation of motion, we can use d by dt of dou L by dou theta here, because degree of freedom here is theta. We can express all other deflections in terms of theta. So here it is dou L by dou theta dot minus dou L by dou theta is equal to 0. This is the equation of motion formed by using the Lagrangian. Let's find out the kinetic energy and potential energies of the system. First thing, for finding out the kinetic energy, we will have to know the deflection. First thing, rotational deflection of the disc and horizontal displacement of the disc. So rotational displacement we can take theta. It is the basic degree of freedom. Let's take the lateral displacement as x and find out how x can be expressed in terms of theta. So if this is the disc and A is its diameter, if it undergoes a angular displacement of theta, its horizontal displacement will be x. We can express x as A into theta. Now we can find out kinetic energy. First thing, rotational kinetic energy of the disc, which is given by half into mass moment of inertia J into omega square. Omega is the angular velocity of the disc. It is not the natural frequency of the system. It's the angular velocity of the disc plus the translational kinetic energy of the disc, which will be given by half its mass into its velocity square. Velocity can be given as translational displacement x dot whole square. Putting the given values, we get kinetic energy to be ma square by 4 into omega can be written as theta dot whole square plus x can be written as a theta. This will give us x dot is a is a constant value, theta dot. So we get m into, we have a theta dot whole square, which gives us a square theta dot square divided by 2. Adding these two terms, we get 3 by 4 ma square theta dot square. Now let's find out the potential energy. Potential energy of the system is possessed by the spring when it is compressed due to this disc. Now the spring has been attached to the disc at a distance d from here. If this is d, this one's a, the total distance is a plus d. The spring is attached over here. The linear displacement of this spring with stiffness k will be a plus d into theta. When it rotates by theta, the translational deflection here will be a plus d into theta. If let's say xs is the compression or the elongation of the spring, it will be equal to a plus d into theta. Remember, we have taken it towards the positive direction, but x can also be into the negative direction. Theta can be clockwise. Now finding out the potential energy, we have potential energy is equal to half into stiffness of the spring into its displacement square, which is equal to a plus d whole square k by 2 into theta square. We have the kinetic energy and potential energy of the system. Let's find the Lagrangian now. We can write the equation of motion directly, d by dt of partial derivative of Lagrangian. Lagrangian is the difference between the two, kinetic energy minus potential energy. And we need to calculate dou L by dou theta dot. So the only term which will have a derivative here will be this term, and the derivative will be 6 by 4 ma square theta dot minus, we have to take derivative of L with respect to theta in the second term. So here we have a negative sign in the equation of motion. We also have a negative sign from Lagrangian itself. So it is minus theta square derivative is 2 theta, and with the coefficient we get a plus d whole square into k theta is equal to 0. Solving this further, we get 3 by 2 ma square theta double dot minus minus becomes plus a plus d whole square k theta equal to 0. So we have the mass equivalent here. Let's name it m star, and stiffness equivalent here. Let's name it k star. Natural frequency omega n as per its definition is root over k star upon m star, which is equal to root over a plus d whole square k divided by 3 by 2 ma square. Rearranging the terms, we get the natural frequency to be omega n equal to root over 2 into a plus d whole square capital K divided by 3 ma square. Let's mark the answer. So the answer here is option A. To learn more about dynamics and formulation of equation of motion, you can refer to the NPTEL video Module 1 Lecture 3 Dynamics in Phase Space from the course Lecture Series on Classical Physics. It's by Professor V. Balakrishnan. He is from Department of Physics, IIT Madras. I hope the solution will help you clear your doubt. Thank you.